third speaker is Guanyu Su, and he will talk to us with that title question, How to Approach a Stranger, the Story of Nucleate Boiling in Annular Flow.
Yep.
Okay.
Thank you, Professor Yudis. All right. Good afternoon, everyone. My name is Guanyu Su. I'm a 6th-year PhD student working with Professor Bongiorno in the field of thermohydraulics for nuclear reactors. So today, I would like to present you a story of how I approach a stranger, which is the nuclear boiling. So before I go to the details of my research, I would like you to think about two questions with me. So the first question is, why do we choose boiling? Our intuition tells us probably it is efficient in heat transfer, otherwise we would not still use it for cooking after thousands of years. So yes, but since everybody can manipulate boiling in their kitchen, then why bother investigating boiling except for brewing nice coffee and cooking delicious pasta? Well, that's because boiling has so many different phases. It has our familiar phase. It also has other phases make us think, wow, this is not the usual boiling we have known for a long time. So this is the reason why I call boiling the closest stranger in my life. So what we have known so far about boiling is pretty much at this steady state, low heating power conditions, such as when we are cooking pasta. We can predict everything about that. But when it comes to extreme conditions, all these traditional theories fail in predicting the heat transfer process. The prediction comes with large uncertainty. Unfortunately, these extreme conditions puts the limits to our reactor power. So one of the examples is the critical heat flux. That is the highest heat flux we could achieve with nuclear boiling. So it happens when these nice individual bubbles, they merge into a complete vapor blanket, which deteriorate the local heat transfer, so the heating wall temperature shoots up. This is a nice video of critical heat flux recorded by my colleague Andrew and Artyom. We can see the heating wall temperature shoots up very quickly around these red spots. So the other example is boiling under extremely fast power input. So just imagine, what if our reactor power shoots up like this in a postulated reactivity initiated accident? What would happen to boiling? So this is what I investigated during my master. So let's focus on the heating surface recorded from a high-speed video here. Instead of seeing several bubbles, we will see hundreds of bubbles popping out at the same time in a very small surface area with only 1 centimeter by 1 centimeter. So this is at transient boiling. In this presentation, I would like to focus on the third extreme condition that's under confined environment, for example, such as this liquid film in annular flow, which happens at the close to the exit of the reactor core in a boiling water reactor. So as I mentioned above, without thorough understanding of these boiling under extreme conditions, we cannot get advanced reactors in the future. So now let's gradually move toward my research. So what I'm showing here is a typical boiling channel in a boiling water reactor. So liquid water enters the channel at the bottom. There's a lot of liquid. As it flows upwards, it gradually boils. It is heated up by the fuel rod, and eventually, when there is a lot of steam generated, it merges into a vapor core, and it will eventually reach annular flow at the top of the channel. So in annular flow, the convective evaporation dominates the heat transfer, which effectively cools down the film, the temperature of the film, so that the nuclear boiling criterion is no longer satisfied. We will not see boiling anymore in the annular flow, unfortunately. Well, this transition from nuclear boiling to convective evaporation is called suppression of nuclear boiling. So my PhD research aims at finding out under what exactly circumstances that suppression of nuclear boiling happens. In order to do that, I have to measure two important parameters. One of them is the thickness of the liquid film, which is measured by the liquid film sensor we developed in collaboration with ETH Zurich. So this is the working principle. Basically, each liquid film sensor consists of 2 electrodes. So by measuring the current circulating from the transmitting electrode through water to the receiving electrode, we can infer the thickness of the film. And this is how the film sensor looks like. So this film sensor gives us the measurement of the liquid film thickness in 2 directions, the longitudinal direction and the transversal direction. This is a quasi-2D measurement. The other important technique I'm using is the infrared thermography. So this infrared thermography gives us another important parameter, that is the heating wall temperature. And this is the This video shows the test section for the infrared thermography. So it consists of a flow channel sandwiched in between two flanges. And there are two major pieces. One is this blue piece that is a U-shaped channel group with a square cross-section. And the opening side is closed by our specially designed infrared heater. So by recording this infrared emission from our specially designed heater through an IR camera, we can infer the heating wall temperature. So now let's have a look at some amazing results. So this is the measurement along the transversal unit of my liquid film liquid thickness sensor. So what we are seeing here is from one side of the channel to the other side of the channel, and this is the film thickness direction, and this is time. So instead of expecting those smooth, nice liquid film, what we are seeing here is highly disturbed liquid film. We see this large spike of water showing up periodically. This large spike of water is called disturbance wave. And this disturbance wave is the signature of thin film in annular flow. And this disturbance wave do not only impact the local flow dynamics of the liquid film, it also impacts the local heat transfer, and which is reflected by our heating wall temperature. So this is a 2D heating wall temperature measured by the infrared thermography. And at the bottom, we'll also see a dynamic plot of the average temperature along this curve. So at this condition, I'm imposing a constant heat flux. But instead of seeing a constant wall temperature, we're seeing this periodic rise and drop of heating wall temperature on top, so which is faithfully recorded at the bottom. Well, the takeaway message is that these disturbance wave induce the wall temperature oscillation even at constant heat flux. So with this superior observation and superior understanding from the advanced imaging techniques, I was able to reconstruct the physics through this transient 1D model. So let me show you what is happening here. So we have this plot, this dashed vertical line represents a liquid steam interface, and this vertical solid line is the heating wall. So in between, that's our liquid film. So I can resolve the velocity profile, which is this blue curve, and also the temperature profile. This is the red curve in this liquid film. When film thickness is relatively thick, we see this velocity profile is relatively low, which results in high heating wall temperature. Conversely, when the film thickness becomes very thin, the velocity goes up while the heating wall temperature cools down because better heat transfer. Now let's look at something that can move. So what I will show here is an instantaneous velocity and temperature profile on the left. On the right-hand side, I'm comparing the instantaneous simulation of the heating wall temperature with the instantaneous measurement of the heating wall temperature. So what we can see here is very good agreement between the simulation and the measurement result. And this terrific result really encouraged me to further simplify model into some semi-empirical correlations so that we can easily apply them into those daily calculations or design process. So which is shown here. This is the empirical models I developed for predicting onset and suppression of nuclear boiling. So basically what I'm plotting here is the measured result versus the correlation prediction. So whenever these dots, they line up in this 45-degree line, it means we achieve a good agreement. So from left to right, we have dimensionless heat transfer coefficient, which I achieve plus minus 5% accuracy, and then the suppression of nuclear boiling heating wall temperature, suppression of nuclear boiling heat flux, which I achieve plus minus 15% accuracy. So I'm telling you these are very high accuracy because if I'm going to use, if I use old model to predict this, we easily get more than 40% uncertainty when predicting this suppression onset of nuclear boiling. So eventually, the mysteries of the strangers, which is nuclear boiling in annular flow, are solved. And these novel database and models I developed will lead to a better boiling water reactor design in the future. And for those who are interested in my details of my research, this is my thesis defense coming up in 2 weeks. You are very welcome. And with this, I would like to take any questions and comments.
Thank you very much. Thank you. So, questions? So I could ask you to clarify You showed us these time fluctuations on the thickness, on the temperature. Can you also explain a bit more on the reason of this certain periodicity in time that you see in wetting, in film thickness?
Sure.
Evolution, yes.
Sure, it's a very good question, thank you. So for the oscillation of the film thickness, it basically comes from the vapor core. When it is shearing with the liquid film, it gradually accumulates the liquid in front of it. And after a certain distance, then there's a shear stress, there's a force balance between shear stress, gravity, and surface tension and momentum force, and all these, the balance, so that it forms a periodic appearing of this liquid film. Yes, and with this oscillation of the liquid film, then the velocity profile, as I've shown, it will vary according to how thick is the liquid film passing through the heating surface. That will change, vary also the local heat transfer. Then we see this oscillation of temperature.
Very good. Good. Any further questions? Right. So let's thank Guanyu Su again.
Thank you.